All right, let's get started. So, any questions first? Okay, good. Today we're going to talk about general mole balances. So now's the part where we kind of go back to the beginning of the book, and we're going to start following along with Fogler. Before to now, we kind of started with chapter 3, which talks about rate equations, and then we jumped up to chapter 9, which talks about reaction mechanisms. Now we're going to kind of be back at, again, where Fogler starts, which is with a general mole balance. So if you have some reaction volume, right, you can have flow in or out, possibly. And then, of course, inside you have some generation term, GJ, indicating that species are either generated or consumed. So if we go back to our standard mass balances, right, we have accumulation is equal to flow in plus generation minus the flow out, right? And so if we put that mathematically, what we get is that the change in the number of moles of each species with time is equal to the flow of that species in minus the flow of that species out plus the generation of that species. And of course, keep in mind that you can have multiple streams coming in and you can have multiple reactions inside that can all be generating or consuming these species. So G is not just the generation from one reaction, but from all the reactions that could be occurring simultaneously. Okay, so if all of the variables are uniform, in that reactor volume, then this simplifies, or G, I should say, simplifies to just being the rate times the volume, right? Because the reaction rate, as we've looked at, depends on things like concentrations and temperatures. So if the concentrations and temperatures are constant throughout this reactor volume, then the rate at each individual piece of that reactor is all the same, and you just get the rate times the total volume. In reality, though, each one of these can be separated into a sort of differential cube, right? Where you have some small cube of volume, and within that, you have that the rate is specified by the conditions inside that cube. So again, you have concentrations and temperature are typically the things that we write rates in terms of. And so if I'm writing this out more generally, rather than writing it this way, which requires that all of the system variables are uniform, I can say Gj is simply equal to the integral across that volume of the reaction rate at those conditions times, again, that differential volume dV. So rewriting this, any questions on this equation? Notice I haven't made any assumptions thus far, right? I haven't told you if we're talking about a batch reactor or flow reactor, it doesn't matter. I haven't told you if we're writing the rate in terms of per unit volume or per catalyst. That's about the only other thing that I've said, right, is this has to be written in terms of per unit volume. Later we'll have one of these design equations that's instead written by per weight of catalyst, just because it's a more convenient system to write rates in if you're dealing with catalyzed reactions. So again, generally speaking, we can evaluate this equation to determine either based on a rate equation that we got from a mechanism or from reaction data, but we can write this equation to determine what's changing with the flow in versus flow out, right? So now let's talk about some ideal reactors that you'll use in the class. And we'll talk about what makes them ideal as we go and why they're different from one another and how it relates back to this equation. So what's the simplest reactor we can think of? What did you guys use in general chemistry in the lab? What's that? CSTR. You guys had a flow reactor in chemistry lab? Probably not, right? Batch. Yeah, you had a beaker, right? You charged it, the reaction takes place, and then you got products. Okay, so typical drawing of a batch reactor, right? And so at time equals 0, you got your reactants. And at some later time, you got your products and unreacted species. Right? So let's go back to our equation. Do we have flow in? No. This goes away. Do we have flow out? No. So this also goes away. So you end up with the change. You do still have change, right? This one is not steady state. That's the whole point of a batch reactor. You wait and things change. It's simply equal to, that's all that we have left. So to give you a bit of context, where do you guys think batch reactors might be used? Would you use that for expensive products or cheap products? Expensive. Yeah. The economy of scale kind of dictates that you set up flow reactors, right? That's often what's going to happen. If you're trying to move a lot of material through a plant quickly, you want to have flow reactors, not batch reactors where you've got to unload and reload them. So these are really most often used in industry for things like pharmaceutical drugs, right? Really expensive reagents that are hard to get perfect inside of a flow reactor. So that kind of goes to the next point. One of the advantages of a batch reactor is that you have pretty good control over what's happening. So you put that impeller down, and that makes sure that everything's uniform throughout the reactor, and you don't have very many issues that sometimes you have to deal with, like pressure drop and things like that. So you have pretty good control over the reactor. You guys think liquid phase or gas phase reactions for batch reactors? Liquid phase, yeah. Again, it's often more common. Pharmaceutical reactions often have some pretty expensive solvents that can, but again, usually it's going to be a liquid phase reaction. So maybe this is obvious, but it's in the notes. The longer you wait, the more product you get, right? That's generally true with most reactions. Some reactions you will stop generating product, right? That just means that you've hit equilibrium. And so the reaction rate will slow to 0. But generally speaking, the longer you wait, the more products you get. All right. So if I've got this impeller and it's doing its job, do I have to worry about this cube of volume being different from one over here? Right. And so that means I can simplify this equation into what?
R times the speed.
Yeah, just the rate times the volume. This is, using the language of Fogler, a design equation for a batch reactor, an ideal batch reactor. So he calls these design equations. We'll have a couple more on the board by the end of the period. Remember, and we put this up here before, that the amount of moles of a species, right, can always be related back to a concentration term times the volume. Right. So often you'll see this written with that in mind. So there's two different ways that one can run a batch reactor. So the first we'll call that. The first is constant volume. And that is by far more common than the other one that I'll talk about, which is constant pressure. So yeah, if you're doing a reaction in liquid phase in a beaker, does the volume change? Probably not, right? Unless you were boiling away your water as your reaction took place or something like that. The volume of your solvent's probably not changing appreciably over the course of the reaction. So that's a constant volume reaction. So at constant volume, I can write the following. All I'm doing is remembering that this is true, and then, yeah.
What if the composer has a strong partial molar volume effect?
Say that again.
What if the composer working with a strong partial molar volume effect?
I mean, in what way do you mean?
Like that, as you increase, like if you're having a reaction and the product or whatever had a stronger partial molar effect than the reactant, then you have a change in volume as you produce.
You mean just from a change in density? Yeah, but usually, right, when you're talking about solvents, they outnumber your reactants and products by a pretty wide margin. So I mean, again, this is for an ideal reactor. This is kind of like in physics saying assume no friction. In reality, you're always going to have some change in density. You're right. But most of the time, that's negligible. So the other type, which might be hard to visualize, is constant pressure. So, you know, a beaker exposed to the air is also under constant pressure, but in a different way, right? But I mean, you know, you can imagine a reaction taking place in a piston where as the reaction occurs, the piston moves up, right? And you get a larger area. So here the volume is not constant. And so you can't pull the volume out of this term because it's changing with time. So the volume is inside of this term because it's also changing with time. So that's the only difference is up here, because the volume is constant, it's not changing with time, I can pull it out of this derivative whenever I substitute in to dn dt, this expression over here, which is just concentration times volume. And so you can rearrange this. This is also equal to the rate. But you can rearrange this as simply by recognizing the partial derivative of volume versus time, you can get that expression. So again, its constant volume is much more common, but if you were doing a reaction where the volume was changing and you knew how the volume was changing, it's not that big of a deal. You know, we have the math to handle that situation. So any questions on batch reactors? Okay. All right, so now the reactor that some of you guys mentioned earlier, continuous a CSTR. Now we do have a flow in and flow out. This is often used when you have gas and liquid reagents. You want to get really good agitation between them. So a CSTR helps you achieve that agitation, which can ensure good mixing. It has, as we'll see, maybe later today or Thursday, it requires the most volume to get a conversion of, if you say you want 50% conversion, this has to be much larger than a PFR, which we'll talk about here in a second. Okay, so continuous might give you a hint, but almost always you're going to be dealing with these under what conditions? Steady state. So that's equal to 0. But it's also equal to what? Flow in minus flow out. And we'll go ahead and make the same assumption that we did with the batch reactors, which is to say that everything in here is well mixed. So rather than putting the integral, I can go ahead and just put the reaction rate times the volume, right? But understand that if this wasn't a well mixed system, I could just put in the integral with Rj times dV instead of just Rj times V. All right, so now all of that is set equal to 0. And so we can rearrange to solve for the volume. Because that's how, that's what matters if I'm trying to think about like a chemical plant, right? Is how big do I need to make the thing? So we have flow in minus flow out divided by the rate. And I put a little subscript up there to help you. The conditions inside of this, are they the same as the feed? No. Are they the same as the product stream? You guys sure? If I'm mixing it very well, then whatever I'm pulling out through that product stream is going to have the same concentrations as the reactor volume itself. So you can often think about this as the rate at the conditions of the exit stream. Because the conditions of the exit stream, those concentrations are the same as everywhere throughout here. Because we're not pulling it out anywhere special. We just have a hole in a valve. So when we drain this thing, these concentrations are the same as these concentrations. These concentrations are different, right? They better be, otherwise you didn't do anything. So as another sort of definition, because now we're not talking about, we have a volume of our reactor, but we also have flows in and out. So remember that I can also write a flow in or out as the flow times the concentration times what now is little v, or a volumetric flow rate. Everybody see that? So that is very similar to what we had before, right? The number of moles, concentration times total volume. Here it's a flow rate in terms of moles, concentration times the volumetric flow rate. All right, very simple stuff, right? And that volume equation over there, Fogler also calls design equation. So we're first going to do design equations just in terms of flows. Then the next thing we're going to do today is rewrite those design equations in terms of reaction conversion, which is usually how we want to do things. So what's the third reactor that we're going to talk about? Ideal reactor. PFR, or plug flow